Welcome back from the spring break. I hope everybody had at least a bit of time to relax and to do things that you wanted to do all the time. I was planning to do what I wanted to do for a long time. I wanted to do nothing, but it didn't work out. So I hope it went better for you. Before we start, just a quick announcement. I posted the assignment 3, the last assignment for this semester. I know that currently it's disabled. You can't accept the assignment, but I will fix that right after the lecture. So please have a look and give me feedback. This is the first time this assignment, I really created it in a kind of almost in a rush. So if there's any problems with it, please let me know. That I wouldn't put it past myself to have made some mistakes here or there. Please let me know, okay? Okay. What I want to do today is to follow up on the discussion we had last lecture with David Koppelman giving us an introduction into GPU programming. And he introduced us to the fact that GPUs have a completely different architecture than the CPU side of things. Mostly that GPUs are organized in what at least CUDA calls it warps, where you have several processing units, usually 32 processing units, combined into one single unit. Each of those processing units still can execute their own sequence of operations, but it's most efficient if you make sure that all these 32 processing units in a warp perform the same operations in lockstep. That is because there's only, no matter how many different execution streams you have, the 32 cores, 32 processing units can perform only one operation at a time. So for instance, if you have an if statement, then half of the cores, half of the processing units might take one branch and the other half takes the other branch. That still means that that all of the 32 processing units have to go through both branches in lockstep, but only half of them will apply the results of those operations as needed. So this is completely different from what we have seen from CPUs, where each CPU has its own thread, its own independent execution stream, and there's no need to synchronize things. So we have a need for a different programming model. We have to approach programming completely differently from programming of parallel computing on CPUs. And what I want to do today is to introduce you to a set of tools we have available on the C++ side of things that help us to manage and to cross that bridge between the CPU and the GPU, possibly with one single code base, one C++ code base that can be compiled either on the CPU or on the GPU without modification. And it will work either way. Okay. So that's why I called the lectures GPU Programming the C++ way, but it's more than GPU programming. It's a way of writing code that makes the code portable across different architectures, across different programming models. Here's just a slide that gives you the 9 most recent, biggest supercomputers we have available to ourselves. The current generation, well, nowadays the upcoming generation is probably already the current generation. And the interesting thing here is that you have 9 machines, and those 9 machines require you to apply 9 different ways of programming. There is OpenMP3, there is CUDA, there is OpenACC, there is HIP, which is the AMD accelerator-based programming environment. There is the DP C++, which is the Intel C++ compiler. There's OpenMP5. So you have all kind of different programming models that all require you to do different things in code. So in theory, if you have an application that should run on all these platforms, you would have to write 5 different or 6 different C++ codes, one for each of those machines, which is tedious to say the least. Just to do some analysis, let's assume a typical HPC production application has around 500,000 lines of code. But that's by no means the limit. There are very large libraries like Trilinos or E3SM libraries that go into the millions of lines of code. And those are just libraries that are being used by the applications. If you the general assessment is that in order to move an application from one programming model, from OpenMP to CUDA, or from CUDA to HIP, or anything like that, you have to rewrite about 10% of the application. If you put that into contrast to what a normal mere mortal software programmer can do, well, the statistics say that programmers usually produce 10 lines of code per hour, which is really a very optimistic assessment in my experience. That means that you produce about 20,000 lines of code a year, and that means that just switching the programming models costs multiple person years for every single application, something we can't do. As it looks like that the set of programming models even will expand. So there are new architectures coming online all the time. There are new programming models being developed, and all of that is a pain in the neck for the application developer, because who is an application developer nowadays? It's a domain scientist, right? They want to solve their problem they have at hand, and writing code for them is just a nuisance. So they don't want to be able to write code in 5 different flavors of C or C++. What I want to introduce to you today is a library which is called Kokkos. Kokkos is a C++ library that was developed over the last 8 to 10 years in the national labs. It aims to give you a data parallel representation or API that you can create a data parallel representation of your algorithms. And is very much aligned with the C++ standard. So almost everything I will introduce you today will be very, very familiar to you, because that's what we've been talking about all semester already. But the main idea of Kokkos is to create a library that exposes one API to the user, one single set of interfaces, but the library itself does the translation to the different, what they call backends, at compile time, essentially, partially at runtime, so that you can write code once in C++ in certain ways, and the library will make sure that this code you provide will run properly on various architectures, on various programming models. In addition, it gives you a lot of libraries that have been written on top of Kokkos, math libraries, tools for debugging, profiling, tuning, many utilities that you can integrate that with Fortran or with Python or with other languages. So it's a fairly large infrastructure that has been created by the guys at the labs. It's open source nowadays. You can download it from GitHub. It is pre-installed on the Docker images that you're using for the assignments. So if you want to play with it, it's available there. And it's used very widely. What I want to do today is to introduce you to, well, one thing I want to do today is to introduce you to that Kokkos API, so that you get a feeling what you can do in C++ and how you can write code that is portable across programming models. So it will be kind of a, you will be feeling like drinking from a fire hose, because essentially Kokkos is a very large library, and all I can do is give you a rough, very quick general overview about what the library can do, and give you some very small, simple examples demonstrating the capabilities. So, as I said, Kokkos is a library that is intended to be used by applications, by scientific libraries, by frameworks, tools, and so on. And all of them use a single API to encode their algorithms. And Kokkos itself has various backends that allow for the code to be compiled on different architectures, on different systems, and still run performant on all those systems. So the main selling point of Kokkos is what they say: we are portable in code and performance. Just another slide I stole from their introductory tutorial slides. What we will look at today is kind of the Kokkos core, is the underpinning thing that makes up Kokkos. But they have many things on top of it, like remote operations, predefined Kokkos kernels for mass, for matrix operations, BLAS kernels, graph kernels, and so on. A bunch of tools for debugging, tuning, profiling, and some support, extensive documentation, extensive tutorials, and so on. So you will find a lot of material online if you are looking for it, if you're interested. So as I said, the idea is that you write code once, and at compile time, things are decided. You decide on what architecture you want to run things. It could be just a normal multi-core system. It could be an accelerator processing unit. It could be some combination of CPUs and GPUs. So what we will look at today is how the computational bodies or kernels are passed to the Kokkos runtime, how the work is mapped to execution resources. We will look at some examples demonstrating parallel for and parallel reduce, and we will do that using a simple example. One word of caution: the Kokkos people use the word parallel patterns. That's nothing else than what we were referring to as algorithms. So whenever the slide says patterns, read algorithm. Or whenever you look at the Kokkos documentation and it says here is a pattern, just as nothing else but what we have introduced in this course as parallel algorithm. Okay, so let's start with some simple example. In the sequential case, let's say you have a bunch of atoms. You want to invoke a certain function, in this case calculate forces on each of those atoms in your system, because you want to figure out what the behavior of the overall system is. For that reason, you have to calculate all the forces and do different things. So you have a simple loop that goes from 0 to the number of atoms and calls that function for you. Two things are kind of self-evident here. First, we have seen that before, right? I always introduced things in the examples I showed. Here is a sequential loop, we want to parallelize it. The other thing that is interesting in this context is, as I said, what Kokkos or what GPU programming means is that you have arrays of data and you want to invoke the functionalities on that data, like that calculate force function, for each of the elements in that array. And the best way to do that on GPUs is by assigning one processing unit in a warp to one element of your array. So this will not work on the GPU properly. On a CPU, it might work if you kind of split it up into chunks, and we have seen how that works. But on a GPU, you want to call that calculate force function for each of the array elements concurrently on all processing units in a warp. So instead of slicing things vertically, if you want, you slice things horizontally by assigning 32 array elements at a time to each of the processing units of your warp, and then you pick the next 32 elements and then the next 32 elements. Always one element per processing unit at a time. So Kokkos maps all of that to execution resources, where execution resource is really just the hardware that is performing the operations. You can think of it that each of the iterations is an independent unit of work, and they call it computational body. It's that kernel you want to run for each element in your algorithm. We have seen these bodies in the parallel for loops as well, right? We were passing some lambda to the parallel loop and said, okay, for each element, call that lambda. It's nothing else here, just that the lambda or the functional body is called is invoked in a certain way that is determined by the architecture the thing runs on. So we have an iteration index which identifies a particular unit of work, and we have a range of those indices which gives you the total amount of work. Nothing surprising here. So what Kokkos does, it manages the mapping, orchestration, and assignment for you. And that is very similar to what I said before, right? We saw that scheme that we said, okay, when I have a problem to solve, I want to parallelize, I first have to find the subproblems I want to represent, and then I need to somehow assign that to threads. I need to orchestrate the threads, the interrelationship between those threads, and I have to map things onto the concrete hardware. Before we said, okay, use HPX for the lower part, for the three things below when it goes to CPUs. But in the Kokkos way, in the Kokkos library, the same is done essentially, but this time in a more platform-independent way. So how do we give the computational bodies to Kokkos? Well, same as before, we use function objects, which is a very common pattern in C++. We have been using it in these lectures many times. So let's review that just to give you an example. A function object is a C++ type, arbitrary C++ type, that has an overloaded function operator. It's an operator parenthesis, and if a type has that operator defined, that means that any instance of that type can be invoked as if it was a function. And whenever it is being invoked, then this operator is used as the invocation, as a body of that invocation of that function. I have talked about that before, just to remind you. So how do we assign the work to that function operators? How do we do that? Well, we define that function object, create an instance of that function object, and then we call parallel for. In the simplest case, just with a number of iterations, and that parallel for will invoke the operator of that function object num of iteration times, somehow mapped onto the computational resources. If you use Kokkos on the CPU, that will probably do something very similar what we have seen for the parallel algorithms. It will chunk up the work and will assign a piece of the chunk, or each of those chunks, to one of the cores. On the GPU, it will do something completely differently. It will chunk up things differently and will make sure that the work is distributed across a VARP in the most efficient way. So the work items are assigned to the function operator. So essentially, you put the code that you want to run for each of those elements in the array inside the body of your function operator. Obviously, parallel for will not care about execution sequence, so things are not sequenced anymore. Same problem as with standard algorithm parallelization. You have to be aware of race conditions. So these can happen. There is no execution order enforced, which makes sense because you want to run at least as many elements concurrently as you have core processing units in a VARP. And there can be certainly race conditions between those because those are independent threads, and if you access some global variable, that calls for trouble. So, but it's nothing new. It's really the very same thing as we have discussed before. So let's complete the picture. Let's say I want to invoke, I want to compute the forces for each of the atoms, and I want to assign whatever comes back from the calculate forces to an array element that is identified by the current index. And you already see that this function object, the function operator takes one argument, which is the index into the index of the iteration that identifies the element this operator should be invoked on. Otherwise, it's nothing special. It's really just a C++ type that can be used as a function object. You might say, okay, how do I use it? Well, as said, you create one of those instances, you initialize it from your data you have somehow defined, and then you invoke Parallel 4, and Parallel 4 will do what you want. You might say, hey, why don't we use Lambdas? Sure, you can use Lambdas. The same thing can be done with a Lambda. Instead of defining your own function object, you can use the C++ syntax for a Lambda, which is a nameless function that takes one argument as before, and the body is exactly the same as we had before. And the only thing we need to take care of is that capture. And I will talk about that capture clause in a second. I don't know if I have talked about that, but a Lambda in C++ is really just syntactic sugar. It's a way to tell the compiler, please generate a function object for me. Because a Lambda is nothing else but a function object with an undefined name. Just to give you to explain that a bit more. When we have a Lambda, we have some capture clause. We have arguments, and we have a body. Right? So when the compiler sees this construct, what it does, it creates a struct with an unknown name, gives it a function operator. Let's say our return value is R. Then that function operator will have a return value of R operator. That's the arguments. It will put the body here. And whatever is in the capture will be turned into members of that type. So you have a clear relationship between the capture, which is the members. The body is just copied over into the body of that operator. The arguments are used as arguments to the function operator, and the return value is used as a return value of our operator. And that's it. So that makes Lambdas really just a simpler way of defining a struct without defining a struct that has that function operator. That's why there's a clear equivalence between using the function object as we did it here, where we have to define that type separately, tediously, or we can write it as a Lambda, which does exactly the same thing. Now, the equal sign as a capture is a special way of saying, please capture everything my body needs by value. Copy everything into the function object. Copy it into the function object when you create the Lambda. So all the captures are copies of whatever is defined outside of the Lambda object. And that is and we will see how that is very important because, look, this code runs on the CPU. And we want for the body of the Lambda to run on the GPU. But as we already discussed, GPUs and CPUs have completely independent memory spaces, address spaces. So you can't just create a variable in the GPU, in the CPU memory space, and in the CPU address space, and access it from the GPU. That is not possible in general. So you always have to copy things over from the CPU to the GPU before you can actually access that. That's why capturing by value is very important, because it will capture all the values in the Lambda, and we will see how that automatically will transfer or help us transferring things to the GPU, so that the body can actually work on the copy of the data that was copied over into the GPU address space. So, yeah, as I said, in Kokkos, when you want to be portable to GPUs, the best is always to capture all variables that are needed in the body of the Lambda by value. You have to be a bit careful, though, if you want to capture large data arrays like vectors or any other C++ data type that might contain a lot of data, then these things will be deep copied into the capture, and that is probably not what you want. And Kokkos gives you facilities that allows you to avoid that and still have copy semantics. Okay? Any questions so far? Does it make sense? Okay. Okay, so let's do a small example. We have done integration, discrete integration before, so let's do the same thing. We want to compute the integral of a given function from a lower to an upper range, and we want to do that using Kokkos. Well, the easiest way to do that is, well, without Kokkos. This is really just the sequential way of doing it. It's a loop from 0 to the number of intervals, and then you compute the area for each of those rectangles underneath the function, sum it up, and in the end you multiply with the width of your rectangle, which gives you the overall approximated integral for that given range between lower and upper. No surprise there. So how do we parallelize that with Kokkos? And how do we parallelize it correctly? And this is a tricky part. But many of the things we will stumble across, we have already talked about in the CPU context, just that in the GPU context, there are more problems we have to be aware of. Okay, so let's parallelize it just by using the same body of the loop as before, but this time we capture it in a Lambda and pass that thing to parallel 4. Just tell parallel 4 that's the number of intervals I want to use, and that is my code. Okay, so question is, will that work? Anybody? Well, general rule is if I ask stupid questions, the answer is no. Okay, so you can blindly say no if I ask such a question. It will not work, otherwise I wouldn't ask the question, right? The problem is, why doesn't it work? Well, the thing is, well, there are several reasons, but the simplest and most obvious reason is you have to know that the operator that is generated by the compiler is const by default. That means that the operator cannot change the things that are captured by default. You can make it change things, that's possible, but by default, that operator is const. So in other words, total integral was captured by value, and we are trying to change it. So this will not work because, well, total integral is a constant value. I can't change it. I can't add anything to it. Because the captures are const by default. That's something you have to remember. Okay, so many students would come up with the idea, hey, let's use a pointer. Let's just, instead of capturing our total integral, we capture the address of that total value in the Lambda, which is okay. I can capture that. And then inside the Lambda, I use a pointer and dereference it and do the addition. I kind of work around the system, right? I tricked it. Because instead of capturing the value itself, I capture a pointer. And since I'm not changing the pointer itself, everything's okay. Well, first, don't use pointers, right? That is the thing I'm trying to tell you almost every lecture. So this is the wrong way to do things. But there's another problem, which is much more subtle. And that problem is that the body is running in GPU address space. So that pointer, the integral pointer, refers to the CPU address space. So there's no way the GPU can access that memory. So this will not work because this will dereference to something the GPU doesn't know anything about. It's an address that is not defined in the GPU context. And by the way, even if it was working, because I'm running that code on a CPU, I would get a nice race condition, right? Obviously, right? Because this is, I'm sharing the total integral across many threads, and that addition would be a race condition. But we have discussed that in other contexts before, that you can't just capture things or import things into the body and share it between threads. So many problems with that code. Another reason not to use pointers, because, well, you create more problems than you're solving, obviously. for that reason, and we had similar things in HPX before, why not? What we actually want to do is a reduction operation, right? We want to reduce the result of the function invocations in a single variable. And in HPX, we have seen the reduction plus or the reduction operation on the for loop. Here we have something similar. It's just called parallel reduce, which is doing very similar things. That in addition to you pass an additional argument to your parallel reduce, which represents a variable that has to receive the results. And that variable is then passed on to the body as an additional argument, as a reference, so that the body can change it. And in this case, it will not pass in the actual total value. It will pass in a thread local copy of that. So each of the body invocations essentially receives its own copy of it. So no race conditions can happen. So this is safe from race conditions. And the actual reduction will happen afterwards, after all the bodies have been executed. The default operation on the reduction is plus. That's why I didn't specify it, but that's commonly the case anyway. So the second argument is a thread private value that is managed by Kokkos and that collects data in a thread-safe way so that you don't have to worry about race conditions. And before returning, the thread local variables are summed up and kind of combined using the given reduction operation. So we have parallel for, we have parallel reduce in Kokkos. And that's the two main patterns Kokkos actually implements. There's a third one, which is a parallel scan. I will not talk about that too much because it's really just an extension of the same ideas we have discussed. But that's the three patterns Kokkos exposes: parallel for, parallel reduce, and parallel scan. What you also want to do is to be able to debug these things better, and you can do that by passing an additional argument as a first argument to these three algorithms, which assigns an arbitrary name to that operation. And that allows to identify that operation in profiling tools. When you look at debugging in a debug session, you will be able to see that name, which helps you to identify the piece of code you're looking at. So it's a thing you should always do when you're using Kokkos. And by the way, HPX allows you to do that as well. I haven't talked about that. It's always a good behavior, a good idea to pass in some identifying information that allows you to help debugging things. Tracing will use that name and so on and so on. So you can identify the code that actually went wrong when you're looking at it in the debugger. Okay, so let's summarize so far. So it's very similar to C++ standard algorithms. Well, a bit different, but we will see how you can actually turn that into something very, very familiar to us because I will introduce you to an additional library that allows you to connect Kokkos with HPX. So you can actually use Kokkos as part of an HPX application, and you can use parallel algorithms that we introduced in HPX to actually run things on the GPU. Okay, questions so far? I think it's kind of understandable. There's nothing very, very complicated there. Always keep in mind the GPU architecture and why do we have to jump through all these hoops? Because GPU architecture is completely different from its essence, from the execution semantics, if compared to CPU parallelization. Okay, so let's talk about Kokkos views then. Let's do a simple DexPy, so a vector scaling and addition operation where you have two vectors. You multiply one vector with a constant and add another vector to it, which this code is kind of straightforward. What I've done here, again, to avoid capturing the whole array, I captured just a pointer to the array. And we just realized, well, this doesn't work, right? It doesn't work because X and Y actually reside in CPU memory. And when I run this code on the GPU, that body will be invoked on the GPU. And X and Y don't exist on the GPU. So how do we solve that problem? We need a way to store the data of arbitrary dimensional arrays, in this case just single dimensional arrays, but the same is true for arbitrary dimensional arrays, in a way that we can communicate the data transparently to the GPU and access it from the CPU as well. And that is done using special types introduced by the library, which are called views. A view is an abstraction that is a very lightweight representation of an array. It's nothing more than a pointer and a bit of metadata. So you can copy views around without copying a lot of data, because copy operations on Kokkos views are shallow. They don't copy the underlying data, like when you're copying a standard vector, the whole vector is being copied, right? All the data that is stored in the vector is copied. When you're copying a Kokkos view, you don't copy the data, you just copy the pointer to that data. And that allows us to capture Kokkos views in Lambdas easily, because, well, it doesn't cost anything, and it gives us access to the specifics of the GPU CPU translation in a way as we will see in a moment. So in a simple case, what you do, instead of allocating an array, you create a Kokkos view, in this case of one dimension, because it's just a double pointer, and I will explain that syntax in a moment. We create two arrays from some data. So x and y will refer to data somewhere else. And then we can capture x and y into the lambda just fine and access the elements using the parenthesis operator on x and y and do the computation we need. Please note that those views have been copied into the lambda, okay? Without all the data being copied. It's really just the view that is being copied there. So they're very lightweight. Think about them, a pointer plus a size plus some metadata. So a couple of bytes essentially. So we can copy them freely into our function objects. Views can be multidimensional, from 0-dimensional, which are essentially scalars, to 1, 2, 3, 4, 5-dimensional data, as many as you like. The number of dimensions for a particular view is defined at compile time. That also means that you can allocate a large array and put a view on top of it which has a different structure from the underlying array. You allocate a one-dimensional array and then you say, hey, this is actually a 3-dimensional view to that array, which turns that one-dimensional array into a 3-dimensional tensor you can access with 3 indices. Arrays are rectangular, always. They are not ragged or anything like that. And the sizes of dimensions set at compile time can be set either at compile time or at runtime. And the way you do that is the following. You pass one template argument to the view that, don't take that literally what's here. The view doesn't contain a triple pointer to a double. What this means is, this is a view that holds doubles and it has 3 runtime dimensions. Okay? And I'm passing, when I initialize my view, I'm passing in the size of these 3 dimensions so that the view knows what are the dimensions of my view. But so in this case, we have 3 runtime dimensions and no compile time dimensions. What you also can do, you can say, okay, I want to have 2 dimensions defined at runtime and 1 dimension is fixed at compile time. I know that in this dimension it's always 3, right? For AI applications or so, they have very often certain fixed sizes for filters and things like that. And in this case, you specify the size of the compile time dimension in that weird array syntax. Again, this doesn't mean I have a double pointer to an array of this size. This just means I have a view that has 2 runtime dimensions and 1 compile time dimension, where the compile time dimension n2 is a constant which defines that dimension. And in this case, I only specify 2 runtime dimensions when I create it, and that gives us a 3-dimensional view in the same way as before. Well, you can combine that in any other way with 1, or if you have 3 compile time dimensions, you can do that as well. Again, don't read that literally. Don't see that as, hey, I have a triple pointer to double, I don't even know what that is. No, it's a way to represent the idea of I have that many runtime dimensions and that many compile time dimensions. And then I can access any of those data arrays with 3 indices, I, j, k, and either assign something to it or read from it. So the view gives you a special way of accessing single elements in that memory space that the view is sitting on top of. The only limitation is that the runtime size dimensions always come first. So aj, if we are looking at the second view, then ij are runtime dimensions and k is one of the compile time dimensions. So you can't mix up, you can't say star and 2 star or something like that. That will not work. The compile time dimensions have to come last always. But this is no news, because even if you know a bit about C arrays, there you have the same limitation, right? You can have only as a certain amount of runtime defined dimensions, but the last dimension has to be compile time if you have compile time size dimensions. Same thing. Okay, to remember is that allocations will not happen implicitly in Kokkos, never. It's always up to you when to allocate data and how to allocate data. So there are no hidden allocations. But copy construction and assignment are shallow, as I said, like pointers. So you can pass views by value, no problem. And the memory a view refers to is reference counted. So it will be deleted automatically when the view goes out of scope. So you don't have to worry about deleting data, which is good behavior, as you know from standard shared pointer, right? Very, very similar. You have an object that holds a pointer, and when the object goes out of scope, the memory will be released. Just as an example, I have 2 views, A and B, all of the same dimensions. I can assign A to B, that works. I can create a new view from B, which I call C. Then I access B and C, and I write a 3 into the element of C02, which means I have actually changed all 3 elements, all 3 views, right? Because when I print A02, I will get the 3 printed, because it really references to that array. It doesn't copy the array data, it really just copies the shim that represents that array in your execution context. Okay, so just to summarize, accessing a view size is done using a special member function extend. You can access the size of compile time dimensions using the member function static extend. You can get the raw pointer to the underlying data by calling data, which is very similar to standard vector. And you can access a label you assigned earlier to the algorithm using the label function. So just as an example, you have a view, you can ask it for its dimensions, and it will give you the dimensions you defined. So the runtime dimension will be n0, and the compile time dimension will be 5. If you want to look at the compile time dimensions only, you can do that. And as you can see, this is a compile time constant. So you can do that evaluation at compile time. That's why it's separate from the plain extend function. You can ask for the data. You can ask for the label, things like that. So nothing unexpected here. Really just for the completeness of the picture, I'm giving you these facilities a view exposes. Any questions about views? Does it make sense to you? Yes?
There is a limitation for the running dimension, the runtime dimension?
The only limitation is that the runtime dimensions have to come first.
Yeah, but the number of dimensions.
How many? No. Probably compiler might introduce, when you have 100 of those, the compiler might start, but
when you write the code, for example, you have 100, you have to put the...
You have to put the stars there, yeah. If you have a 100-dimensional array, you have to put 100 stars here. Good luck with that. I mean, you will not get that right. I mean, nobody is going to do that, right? But for the normal use cases, this syntax is fine. It's a bit unusual, but hey, that's how it is. Okay. Let's talk about execution spaces. Execution spaces are another facility Kokkos exposes, and execution spaces represent the execution mechanism. It represents where the code will be running. Will it be running on a CPU, on a GPU, on that tensor device over there, on OpenMP? Will it run, you just have a type which represents where things will be executed. And that could be on the accelerator, as I said, could be somewhere in the NUMA domain, could be on some core. The interesting thing here, what I want to highlight is that Kokkos supports HPX backend. So you can run Kokkos code on HPX by letting it use the HPX facilities to do the run, the execution on the CPUs if you want. Okay, so how do you do that? If you have a normal parallel 4, that's the syntax I showed you before, then just passing in the number of iterations implicitly means that I'm using a special, what's called a range policy, that goes from 0 to the number of iterations. So it's a simplified way of writing it this way. And as you see, the range policy actually is a template which expects you to specify the execution space where that range should be evaluated. By default, it will use the default execution space, which is configured at compile time. When you configure your library, you say, oh, my default execution space is CPU. And then whenever you don't specify anything, it will use that execution space. But if you want to specify an execution space, we can do it this way. We have some execution space that might refer to the GPU, for instance, or to a particular NUMA domain, or whatever you have. Then you can run your parallel 4 in that way by saying, hey, please run it from the index range from 0 to the number of intervals, but run it wherever that execution space points to. And then this body will be executed in the context of that, wherever that execution space refers to. Well, you have to enable it at compile time, otherwise execution spaces will not be available. On the Docker file, Docker image for the homework, execution spaces are enabled, so you can use them. And the only thing you have to be aware of is that as soon as you use execution spaces, you have to annotate your functions and your function objects with special macros, with special keywords. So whenever you have a function that is supposed to run on a execution space, you have to prefix it with Kokkos inline function. The same for the function operators. That is done because when that code is compiled on a CPU, this macro just expands to a simple inline statement, which doesn't change anything on the CPU. But on the GPU, it expands to some additional directives which tell the compiler, hey, this code has to be compiled to be run on the GPU. This is unfortunate, but nowadays you have to tell the compiler which of the pieces of the code should be running on the host and which of the pieces of the code should run on the GPU, on the device. And the easiest way is to annotate it with both, which means this code you will be able to run this code here and there, which will make the compiler compile it twice, essentially, once for the GPU and once for the CPU. The same is true for Lambdas. For Lambdas, there is a different macro, which is a bit strange because that doesn't look like a Lambda anymore nowadays. Now when you write it this way. But just keep in mind that on a CPU, that macro expands to a simple capture by value. And on the GPU, it inserts these additional directives into the Lambda definition. So there's no other way to do that. So it's a bit strange because the device and host have to go here for the compiler to understand it. And there you don't want to have two versions of the same code, right? And by using the Kokkos Lambda annotation, you will get exactly what you need. But this is just a technicality to understand why we use that Kokkos Lambda everywhere. That's execution spaces, so it's nothing too complicated. The other concept exposed by Kokkos is memory spaces. as we already said, in these heterogeneous architectures where you have CPUs and GPUs and accelerators and special devices, you have different address spaces. Each of those things has its own independent, non-overlapping address space. So there's a memory, the DRAM from the CPU, there is some on-package memory on the device, and so on and so on. And Kokkos uses the notion of memory spaces to identify those, because you have to tell it somehow how things are actually, where are things located. And you do that by passing an additional template argument to the Kokkos view. You say, okay, this is a Kokkos view that has 3 runtime dimensions, and it lives, the memory lives on that place where the memory space refers to. And we will see some examples in a minute. There could be host space, which refers to the CPU. CUDA space is a predefined one when you're using CUDA. CUDA universal memory space is when you're using CUDA universal memory, and so on and so on. So each of those memory regions, independent memory regions in the device, in your machine, is represented by one particular type that identifies that place. Each execution space has a default memory space associated with it. Obviously, right? When you want to run on a CPU, you probably want to have the data located on the CPU as well. So the execution space knows where its data is located. So if no space is provided, no memory space is provided, the view resides in the default memory space. So if you don't pass in the memory space, it will use the default memory space of whatever you configured at compile time. On the other hand, you can explicitly ask each execution space for its memory space. You can say, okay, what is your memory space? And can use that. So in this case, these two things are equivalent because it will use the default execution space, which is whatever defined or configured at compilation time, and will use the memory space that is associated with that, whatever is configured there. Okay, let's use it for something useful. So we have some view that lives on the CPU in host space. That means that we have an address space on the CPU. That orange square represents a view, and that teal-colored rectangle represents the data the view is referring to. Since it lives on host space, both things are on the host side of things. When we use a CUDA space, we still have the view living on the CPU side of things, but it somehow magically refers to the data that actually lives on the device. So you can copy that thing around in the CPU space without dereferencing it, but whenever it gets to executing things, that data that is stored in here is transferred to the GPU, and it makes sense in the context of that address space. So you can work with that data on the CPU side, but not on the GPU side. On the GPU side, but not on the CPU side. I apologize. Does it make sense? That's why it's so important to have views, because it allows you to actually handle things on the CPU, because you usually kick off all the computation from the CPU side, but still have the data residing somewhere else in some other address space without you actually having to know how that is being done. Okay. Let's sum up an array on the GPU. Let's write that code. We have a view which has a certain size. We want to initialize that array from a file. So on the CPU side, we want to go over that array and want to initialize it with some data. And then we use that very same array in the body of the parallel 4, where the parallel 4 is run on the CUDA side of things. Okay, so I launch the body on the CUDA execution space. Will that work? Stupid question, right? No, it will not work. Why will it not work? Anybody? No, the array lives in CUDA space. I'm accessing the array on the CPU side, and I'm accessing the array on the GPU side. So where will it break? Come on. There. Because that view refers to memory that lives on the GPU. So I can't access it from the CPU because it's a different address space. So that will not work. Okay, let's turn it around. Easy. Let's let the view live on the host space instead. So allocate memory on the host. Then I can read the data and initialize my array. And then I can use the array inside my body. Will it work? Well, probably not, right? This time it will break here. But because this time the GPU tries to access memory that is actually living on the CPU side of things. Bummer. What should we do? What can we do? Well, what Kokkos provides you with is what they call mirrors. So it's views that have equivalent arrays on both sides, which are where the two arrays are copies of the same data. So what you do, you have some view on some predefined space, it doesn't matter, and you say, I want to have that data mirrored on the host. And I call the function create mirror view, and it will create a copy of the data if the data is not accessible from the current space. So this will give me two copies of the same data living in two different memory spaces. So I have now two views. One view refers to the CPU side of things. The other view refers to the GPU side of things. And the data is deeply copied. And I just have the view. I still have to copy the data myself. And I will show you in a minute how that works. Okay? So how does mirroring work? I create a view in one space. I initialize it. I create the mirror view in a different space. I populate the host view on the host from a file, whatever. Then I call Kokkos deep copy, which copies the data from the host view into the other view. So I populate my other view, make it equal to my host view. Then I can use my parallel 4. And in that parallel 4, I can refer to the view because that now lives on the GPU side of things. And eventually, if I need it, I have to copy things back because I might have changed data on the GPU side of things. I want to get the data back so I can write it to a file or do other things with it. Please note, it's kind of strange because this is a source and this is a destination. So destination comes first. You can think of it as memcopy, right? Memcopy has the same weird argument sequence that the first argument is a destination, the second argument is a source. So that's a way to deal with these things. So that you have data that you can read and write from the CPU, but you still can run your computational kernels on the GPU side of things. You have to go through these explicit steps. So what if the view is in host space 2 and I call create mirror view? Well, nothing happens. Because if the data is on the same device, you will just create a new copy of your view and both will refer to the same data. So that's safe. So create mirror view will not do anything if the two spaces are the same, which is kind of an optimization. But if I want to copy and allocate new data, I can use create mirror instead of create mirror view, which will always create allocate new memory, and then I can do whatever I need to do with it. However, Kokkos never performs hidden deep copies, so you always have to do the deep copies yourself. All it does, it allocates a memory for you on the appropriate space, but putting the data there is something you have to do. Okay, just in summary, the data is stored in views, which are pointers to multidimensional arrays. The data itself resides in memory spaces. The view abstracts away platform-dependent allocation, because in different address spaces we have to use different allocation schemes, different allocation functions. On the CPU it's malloc, on CUDA it's CUDA malloc, on other devices it's something completely different. In heterogeneous nodes we have one or more memory spaces, so we have to use mirroring to make sure that we can handle these situations. And we have several execution spaces, and we have to explicitly control where the code has to run, which of the pieces of the code has to run where. This runs on the CPU, this runs on the GPU. Okay, Last note, and that is really just a side note, sometimes when you do complicated things, you want to be able to decide how things are being laid out in memory. You want to be able to say, hey, this is column first, this is row first, layout in memory. So column major would look like this, row major would look like this. Kokkos has different layout types that are predefined, and you can use layout types when you define the view just to specify how is my data laid out. Is it column-wise or is it row-wise or whatever? And that's important because of the different execution schemes on the CPU and on the GPU, usually memory on the GPU is laid out the other way around compared to the CPU. So you usually have this layout on a GPU and this layout on a CPU, because that allows you to give row-wise things to your warp. Whereas this is better when you chunk things up in a parallel algorithms on the CPU side, as discussed. So you can specify a layout explicitly. There are different predefined layouts. Layout left is the leftmost index has stride 1. Layout right, the rightmost one has stride 1. Layout left is CUDA space. Layout right is for the CPU space. You can write your own layouts if you want with custom striding, but there are some striding and tiling layouts predefined for you if you need them. Well, I didn't cover many things. I will not go through that. Build system, reduction, multidimensional loops, and so on and so on. So there's a lot more in Kokkos you might want to read about when you want to write real code. I will not kind of go into that here. I just wanted to give you kind of the overview of what I didn't cover, because, well, one lecture is way too short for that. The last I want to do today is to talk about how can you integrate Kokkos with HPX, because, well, HPX is what we were talking about all semester, so it just makes sense to do that, to talk about that. And before I begin, there are two ways HPX is integrated with Kokkos. HPX is available as a backend for Kokkos. That means it's available as an execution space where to run things on. Run it on HPX. But there's also a second integration there where HPX is put on top of Kokkos so that you can use HPX parallel algorithms and run things on the GPU. And the second part is what I want to go into a bit deeper. The first part is straightforward because it doesn't make any difference. You just specify the HPX execution space and it will run there. The second part is a bit more intricate and a bit more interesting, actually. Okay, so there's a special library which is called HPX Kokkos. It's a separate library you have to download and install. As before, it is installed already in the Docker image you have for the assignment, so you can play with that if you want. What does that library implement? It's actually a very thin library, very small library, not much code, but it provides you with very interesting facilities. First of all, it gives you asynchronous versions of the Kokkos patterns. So you have an asynchronous, parallel for, parallel reduce, parallel scan. It gives you an asynchronous deep copy. What do I mean by asynchronous? It means that you can launch that function, and instead of waiting for the function to return to you, it will give you a HPX future. And we talked about futures 2 lectures back. That gives you a means to launch asynchronous execution and synchronize with it later. So you can overlap a deep copy operation with actual computation on the CPU. So while that deep copy is happening, by the way, the copying to the device is one of the big bottlenecks GPU programmers have to overcome, because if you have large amounts of data, you have to copy it back and forth many times, and that is very costly in terms of time. So if you have a means of overlapping that copy operation with actually useful work that you might do on the CPU or on the GPU by having a synchronous version, which just kicks it off, then you do something else, and eventually when the deep copy operation is done, you synchronize with it and can continue, is very useful. What it also has, it's a set of HPX executors, and I will show you how to use those, that forward the work to corresponding Kokkos execution spaces. So for each Kokkos execution space, you have an HPX type that integrates with the HPX infrastructure. We will see how that works. You have a special execution policy that you can pass to the parallel algorithms on the HPX side of things. Remember, we have that HPX execution par, which parallelizes the loop. Here we have a new execution policy that corresponds to invoking the Kokkos algorithms. Those are, by the way, synchronous and asynchronous, and I will give you an example in a minute. And we have HPX parallel algorithm specialization, so that you can call an HPX for loop and run things on the GPU by providing the appropriate execution environment. Just a word about how to do the build system. As before, CMake based. You tell it to find these three packages, HPX Kokkos and HPX Kokkos. You have a C++ file, HPX Kokkos example CPP, which you want to compile into an executable, and you tell CMake that you want to link with these three libraries, and that sets up the build system. So you don't have to jump through hoops to actually use these things. It's very, very straightforward to do. Okay, let's look at a asynchronous parallel 4. How does that work? We have two views, one in host space, one in CUDA space. Then we initialize the data on the host side with 0, just by looping over the result host view and assigning 0. Then we define a CUDA execution space. So we want to run things on CUDA. We copy things over from the host to the device using this execution space by just saying, OK, do it here. And we use a new function, deep copy async, which instead of waiting to finish the operation, it will come back immediately and give you a future, which is good. So we can initialize other operations. We can call Kokkos parallel 4 async. Same parameters as before, just that instead of being synchronous, it gives you a future which represents the execution of that parallel 4. Please note that I'm passing the same CUDA space in here. So in principle, I wouldn't need these futures, because as long as you launch things on the same execution space, they're chained automatically for you. So the parallel 4 will start running only after the copy has finished internally. So I don't even have to synchronize with that. That's why I can kick it off right away. And last but not least, once I'm done with it, I'm copying things back, because I have changed my array, my view. So I copy things back to the host, and I wait for all the operations to finish. Right? I have 3 futures, just wait for these 3. In principle, I needed to wait only for F3, because the others are guaranteed to be ready because of that internal dependency. I just wanted to make it explicit here. And once I have waited for all the futures, well, I can check for the results, and the result should be fine. So you see one way of integrating CUDA with asynchronous operations in terms of HPX, which is really nice because it gives you that asynchrony feeling we need in many contexts. Just a very quick example, same thing, just with a parallel reduce. So the rest is really identical. The only difference is that I'm now calling the parallel reduce async, which gives me a future as well. Otherwise, absolutely the same as before. Okay? As I said, there are HPX or types that refer to Kokkos execution spaces. And those are called executors in the context of HPX. And as you see, we have various things predefined: a CUDA execution space, HIP, SYCL, OpenMP. You can run it on HPX, whatever. So these things are predefined for you. And you have a new execution policy we can use for the parallel algorithms. I don't know who have come up with that weird name, KOK. Somebody else is responsible for that. But anyway, that's probably an abbreviation of PAR, just on the Kokkos side of things. So, and they wanted to reduce it to 3 characters because PAR is 3 characters as well. Don't know, but that's how it is. Let's see how we can use an HPX for each using Kokkos. Same thing as before. A host view, a CUDA view. We initialize it on the host side. Now we copy it synchronously, just for the sake of it, to the CUDA side. Now we use HPX for each with that Kokkos execution policy, and we pass the data to the algorithm. Well, begin iterator, end iterator, and that Lambda. And that will make things run on that execution policy, on the device, because that thing refers to the device. If and only if we tell the execution policy to actually use the CUDA executor as the execution space. And that is done using the .on function on the execution policy. So you say, hey, I want to run it on Kokkos, but I want to use this execution policy, which execution space, which is the CUDA execution space. And by the way, I want to add a label to it. You can do that as well. As easy as that. And this will integrate Kokkos with HPX in a nice way, and will use the HPX for each, the HPX algorithm, which is compatible with the C++ standard algorithm mechanics we are well accustomed to by now, and run things on the GPU. So you can still run things on the GPU completely from the standard compatible interface. You don't have to worry about these parallel for, parallel reduce thingies. You just use whatever the standard has for you, for each. Okay? The same can be done asynchronously, and that's a bit more interesting, because what we do now, you might remember, we can turn HPX parallel algorithms into asynchronous algorithms that will give you a future by passing that execution task to the execution policy. The same can be done here. And if you do that, if you pass the asynchronous execution policy, then this algorithm will return right away and will give you a future which will become ready whenever the GPU side of things is done computing. So you can synchronize on the CPU with GPU execution easily and integrate that kernel that runs on the GPU side with your overall execution infrastructure on the CPU side, which is very nice because you can orchestrate your dependencies in a very nice way. Okay, does that make sense? I know it's kind of a lot, but in the end, if you take a step back, it's nothing new. It's really everything we have discussed already. I'm not introducing new things except for a couple of new names that refer to different things, but the conceptual background is absolutely the same as before. The last example I wanted to give you, we don't have to go through that, just how you can use a multi-dimensional iteration using HPX algorithms by passing a MD range policy where you tell it, okay, one dimension goes from 0 to n, the other one goes from 0 to m. And that will invoke the lambda with 2 arguments instead of 1 argument, because you have 2 indices now, right? Otherwise, it's very much the same as before. So if you want to do the same with multidimensional data, you can do that in the same context, just by using a different Kokkos range policy and pass it to our algorithm as before. Okay, good. So in conclusion, Kokkos is an abstraction library that hides accelerator architectures and idiosyncrasies and allows you to run the same code on essentially any architecture that is available today in the high-performance world. And the good thing is, if somebody comes up with a new architecture, you don't have to worry about it, because the Kokkos guys will implement a new backend that targets that new architecture for you. So you just have to wait for them to do it and poke them and say, hey, I need it. Fix it. The second thing I want to highlight is that HPX parallel algorithms are much more versatile than you anticipated. So they're very versatile and not limited to standard C++ parallel execution. So you can use them for many more things than just what meets the eye on first glance. So we can use it for accelerator parallelization, we can use it for asynchronous operation, even on the accelerators, and so on and so on. Any questions? Okay, well, then I'll let you go. Thanks for your attention. see you on Thursday, I guess.